Without no further ado, let's start our discussion. Okay. So last time we started talking about Feynman diagrams. Okay, so let's continue. And then Feynman rules. So the context was we are interested in scattering amplitude. So scattering amplitude is defined by, let me even write it explicitly. So there is a specification of n final particles, and then specification of n initial particles. And then once we specify theories, this is a theory input. Right? This is theory input. If I put the theory input, and then once I do that, I know what spectral particle I can expect in the initial state, what spectral particle I can expect in the final state, and then we want to be able to compute this. And this is a gigantic function of basically some gigantic function of initial particle momenta, and then final particle momenta. So this is a function of momenta, right? So, therefore, if we take again once the example of our lovely Yukawa theory, okay, then we want to develop a diagrammatic machinery to be able to compute this function. That's the one. And then we will discuss physics. How to, what features of which features of this function of momenta captures which part of the physics. So that's the question. So at second order, for instance, we wanted to look at, I forgot which one we decided to look at. Suppose we want to look at the n goes to nn. So where this thing produces, so let me skip all the details. So alpha is an annihilation operator of the particle, which I call n. It comes with either a minus IPX, and then there was a beta dagger, which is the creation operator for the antiparticle n bar, which comes with plus. Okay, so we talked about this. Now, we already talked about the Wick diagram, and topology and all kind of structure of the diagram is the same. It's the interpretation and usage are different. Okay? So for instance, if I actually want to have this thing, what types of diagram we should talk about? Well, there's this diagram. Suppose time goes, which way time went last time? So this time goes this direction. Why? So I just want to synchronize the diagram with this. So there's the initial particle, right? And then going that way and then turning to the final thing. So particle, remember, the charged fluid and momentum goes together. So I can label P1, P2 because initial states are labeled by momentum. Okay, so I have to use K. K1, K2. And then there's this guy. So this is n, another n, turning into n, and let me call this to be phi. So let me just pi. So this guy produces n or n bar, and this guy, particle name I just call pi. Okay? And by momentum conservation, so momentum comes in, coming out, and then this, you can check that the sum of the two outflows should be same as one inflow. That means that this is P1 minus K1. Okay. There was another diagram. This. Okay, so now P1 actually matched to the K2, so calling P2 matched to K1. And then here, this now becomes, basically I exchange to P1, P2. So here basically it becomes a P2 minus K, right? On top of that, so I call this diagram to be A, and then this diagram to be B, and you expect that both diagrams must contribute to this scattering amplitude. However, you also understand that these two diagrams will make a distinct contribution to the final answer, because as a function of momenta, even though these are the same, for Q, momentum transfer is different, right? So as a function of a momentum transfer, this will correspond to the different function. Hence, you want to keep it. Another two diagram that we talked about was that if I call this vertex to be 1, 2, 1, 2, and then I can talk about a C, which is obtained by doing permutation of these two vertices. And then we had another diagram. In principle, one can get it by taking this diagram and permuting 1 and 2. But once we do, so this one, right, we will have this formula. And so let me just write a second order because we will start the actual computation here. So it's actually good to have it. 2 factorial, and then d4x1, d4x2. And then, so now instead of writing now this, let me actually write a amplitude. So initial, final, I'm just shrinking to this simple notation. And then this one will have a what? So K1, K2, time ordered. Should I just write it out? Should I? Should I? Should I? I should. K2. I pulled it, well, I should have because I already pulled this up. And, sorry. Two, and then P1, P2. Very good, successful. So, and in particular, we want to look at this thing include a contraction. According to a Week's theorem, this thing include a contraction that looks like 1. How many times I'm writing this? Very good. So this contraction, that's what we are looking at, correct? So that thing included a lot of contraction. So this side doesn't change. This is just the operator algebra part. What changes is whether we represent this operator in terms of a Week diagram or we represent this amplitude in terms of Feynman diagrams. That's what's just changed. Okay? Now, the quick point that I wanted to make is that this permutation will make the same contribution because once we do the integral over the vertex locations, anyway, do all the permutations to itself. So therefore, C. The point was C makes the same contribution as A, and then D makes the same contribution as B. In fact, you see this why? Because even if you didn't know, well, it's good to know you have this integral. But as a function of momenta, this thing is literally the same function as that. Right? Same external labeling, same momentum transfer. Same external labeling, same momentum transfer. So it must be the same function of momentum. So you should have a factor of 2. So here, one important point that we I think stated the last time was that therefore in the Feynman diagram, given a Feynman diagram with a specified momentum, and then if you permute all the vertex by n factorial, suppose you're looking at the n vertex diagram, all of them will give the same answer. And that always guaranteed to cancel 1 over n factorial, right? So therefore, here the lesson is that in the business of Feynman diagram, you care about the momentum configuration. You don't worry about the vertex permutation. And then you just need to write down you just need to draw one Feynman diagram for fixed momentum configuration. Vertex are automatically taken care of by this vector. That's good. Okay? So let me not just write onto like that. Okay, so let's actually see why this is actually true. Let's actually see this explicitly why this is actually true. So far I just built up as a bottom up. Yes?
Well, if you permute 1 and 2, then the flow of the momentum between them is. 근데 저 파이가 밑으로 내려가는 똑같으면 모멘텀 플로우 자체는 permute도 달라지는 거 아니에요?
Good. So the question is, if I do it, wouldn't I pick up the minus sign in front? Okay. Basically, that's what you will see, right? So if I permute, then either you can just view it as no, I'm just relabeling this. Therefore, still I'm getting the exact same thing. What you were thinking, I think, was that this, and then I forced to flip it. That's the same diagram as this, right? So I'm not making a like topological modification of that.
그러니까 1에서 2로 가는 거랑 2에서 1로 가는 게 달라지는 거 아닙니까?
What? So how this thing know that it comes from the first initial n with the momentum p1 that turns into the final n with the momentum k1, right? That's how this momentum transfer. That's how you figure out the momentum transfer itself. Not like by saying, oh no, you came from that particular point of space and time. This thing doesn't know, right? There's a particle and then split into these two guys. So only the momentum data is relevant to figuring out the momentum. Does that make sense? But even if, okay, that's not the case, even if you get the minus sign, but we are going to get a Lorentz invariant function of momentum. And Lorentz invariant function of momentum is always the square of the momentum, either in the product. So again, you will see that it doesn't matter. But again, that's not the case. Here it's literally fine. Any other questions? Yeah, okay, good. So let's actually now do this computation, and we will actually see this is a correct thing. Okay? So far, I just made a guess. Let's actually see. So let's compute this. Now, recall that if you have a contraction, let me recall, so this is equal to actually time ordered phi 1, phi 2, because normal ordering piece drops out, and in the case of a scalar operator, so this is just q squared minus m squared. Okay, so you probably have to, more precisely, 1 and 2. So 2 and 1, I flipped. Okay, so that's we talked about. And but also this is a C number. So we also talked about the fact that we can just take this out. So let me just continue this calculation. Okay, and then we have this integral. And then again I can take out the contraction part. Okay, and then K1, K2. I just need to compute this up. Psi 1 dagger psi, psi 2 dagger psi. Okay, so I'm gonna simplify that even more. So I'm about to write down the next line, but let me just remind you of the following fact. So that fact is recall number 1. Is that when we have a one particle state P, right? Our definition, according to our normalization, is that we're gonna act alpha P dagger on this. Okay? So where this alpha P is literally the alpha that appearing here, right? So that's the definition of a one particle state. And so if you see therefore, for instance, a two particle state, obviously it is dagger, P2 dagger, acting on vacuum. Order doesn't matter because this is the bosonic particle, and in fact, this permit. Okay, that's number 1. And then another thing that I want to comment, and then we're going to simplify. So we started out with the 2n and n in the initial state. And then the physics is that, so I need to normal order, but this psi operator contains both alpha and the beta part. The question is which one we are going to use. Well, I know which process I want to compute it. And then in this entire process, my interest is only n rather than n bar. So therefore, when you see psi here, for instance, you have to read this as alpha e to the minus I dot x. When you see psi dagger, you read this as this. Is that clear? I'm not using beta part. That's all I'm saying. Okay? Then, since I need to do the normal ordering, this is annihilation, this is creation. So creation part has to go to the left, and the annihilation part has to go to the right. That's the normal ordering. Okay? So therefore, I can rewrite this as follows. Two, okay, and then contraction part is is this that I know. And now there are a lot of terms, but let me just write this. So vacuum, and then this is alpha k, so alpha k1, alpha k2, so that's from this. And then I need to normal order, so I'm gonna just literally do the normal ordering. So I have to do 1, 2 dagger, 1, 2, alpha p1, alpha p2, vacuum. Did I flip order? No, I did it, right? Good? Are you with me? I actually did a normal order, because I know what it is. Okay, so now we can actually compute that. Oh, what? So let's focus on this point first, because that's literally just the conjugate of the other side. Okay? So,
for the P1 and P2 state, isn't it should be alpha dagger?
oh yeah, yes. Oh, that's why some of you look unhappy. Very good. Yes, it's dagger. Thanks. So let's actually look at that side. So side 1, side 2. So here labeling is according to x1, x2. Alpha P1 dagger, alpha P2 dagger acting on the vacuum. Okay? So let's just look at this piece. Now, if you look at it, so I use the K. Well, okay, here L1 to the minus I, L1 dot x1, alpha L1. So that's this side. Okay, and then so let me actually put it out. As you see, I'm trying to be as detailed as possible, just once and for all, and then I'll go. Right? So basically, you need to compute this. So it is a quick exercise for you to do that to show that by basically, rewriting this as a commutator times the normal ordering, and so on. So this you can show to be the case that L1, comma, P1 dagger, L2, comma, P2 dagger. So first I paired up that, and then second time, let me save this space. And then second time I'm gonna pair 1 with P2 dagger, 2 with P1 dagger, and then everything else is normal ordered. Okay, it's a quick exercise to do. And normal order piece doesn't contribute because if you act on the vacuum, it goes to 0. Okay, so basically this. And you may remember what this is. So this alpha dagger is basically 2 pi q to e, p, and then delta momentum. So basically canceling this entire 1 over 2e and then 2 pi to the q piece. Alright, so therefore, if you plug in this, you have a 2 delta function to finish up the 2 calculation, and basically all you get is basically phase vectors. Okay? So in fact, you can show that this is nothing but e to the minus, because I'm looking in this case, minus I. If I pair up that way, I'm picking up x1 with the p1, x2 with the p2. That's what this is doing. Okay? So basically you're gonna get p1.x1 plus p2.x2, and then you're gonna get another piece, because you have this sum. Second time you get p2.x1 plus p1.x2. That's basically the answer. And this piece is basically the same, but we just conjugate. Okay? Here you can already see a feature that you want to see. So this is manifestly symmetric, if you look at it. This is manifestly symmetric in the exchange of a P1 and P2. Right? There's a relative plus sign here. And that's why you want to see. Because here, n particle, remember there's n, which are bosonic particle in this particular example that I'm studying. Therefore, they have to satisfy bosonic statistics, right? The answer should be symmetric under the exchange, which is guaranteed to be the case. And here too, once you do the computation, everything is exactly the same. So P1 becomes K1, P1 becomes K2, and then again you will see that it's a symmetric under the K1 with the K2, right? Exchange. Exactly the same. Okay, so then I can actually write it down, the answer. So let me do it. So therefore everything is equal to, boom. So now you will have a product of this times another factor that comes from the final part. Okay? So you plug in and then you should do the calculation over 2. Okay? And this is the answer. Times 2, because this, if you actually do the calculation, okay, instead of me writing it down, let me actually not do this. Let me take just one more step to illustrate. Times, because that goes there, and Q. So I'm writing this in contraction. Okay, so I've written down the contraction part. And then I have this too. And then I'm not going to write everything. But basically, you're going to get something like this. So e to the I x1, k1 minus p1, and then k2 minus p2, and then you're going to get this plus p1 exchanged with the p2. Okay? And then you're going to get everything but x1 exchanged with x2. So you have another copy, but x1 is exchanged. So if you recall, this corresponds to basically the diagram A that we talked about. There was a P1 converting into K1 with exchange, which is Q, which we will contract soon. And then P2 turning into the K2 with the contraction of the Q1, which we will do it basically now. So that's A. But then since I exchange the P1, P2, that corresponds to B. And then, so this is the 4 terms, right? There are 2 terms from the initial, 2 terms for the initial. You have contraction of 4 of them. I'm just writing 2, which are related by the exchange of P1, P2, and then the other 2 related by exchange of X1, X2. That's what I'm saying. And so this corresponds to C and then D, which are identical because if we do the X1, X2 integral, it's identical. Okay? So in the end, so this is the explicit proof that why the statement I made was correct, right? So I don't have to worry about the permutation of vertices. This will always contribute to times 2, so canceling out these 2 factorial. Okay, so after once the dust settles, we get the following answer. Yes.
Integration over x1 and x2 should be in front of that propagator.
That's true. Yeah, but so you know.
Just throw the end.
Very good. So this has to come here. Okay, thanks. Okay, so I'm gonna write therefore the following expression, and I'm writing it with an intention because now I want to read off the Feynman rules. So I have this. Okay, good. So and then I have this. And then if I do this thing, what would you get? So that you will get you see, there's a x1, k1 minus p1 plus q. And then if you do the x integral, what did you get? So you should get 2 pi to the 4th delta 4. Let's see if I get that right.
K1 minus P1
Plus q,
minus Q.
minus q, plus q, minus q, either plus minus. Okay, so and then the product, I'm sorry. And then 2 pi to the 4th, delta 4, k1 minus p2, minus q, something like that, right? And then I'm gonna have a term with exchange in q and p2. That will do that.
Then that one should be K2 at the best.
Yes, of course. Yes. Very good. Very good. So now I want to draw a diagram again and then actually do the summation. Okay. P1, P2 coming in. K1, K2. So for each vertex, what you have done, basically this tells that forget about the permutation of vertices. That's what the first piece. So for each vertices here, what you're doing is that you do minus I times g, and then you impose momentum conserving delta function at that vertex. That's what this delta function does, right? And you do the same here. And then for the internal propagator, not external lines, internal propagator, you do this. Okay? So this consists of a product of vertices and then internal propagator. And you have the same thing with P1, P2 exchanged. Okay? So this is already sort of useful to extract the Feynman rules. So if you know how to draw this diagram, for each vertices, there's a strength of interaction of up to minus I factor. Okay? And then you just impose a momentum conserving delta function at that vertex. And you do every vertex appearing in the diagram. Internal propagator, basically almost that, but you have to integrate over the P4Q. Okay? Is that clear? Okay. So let's finish the calculation now. So if I do this calculation, then what I will get is the following. So let's just focus on this. So if I use this P4Q to do this integral, so Q becomes P1 minus K1. So instead of Q, I'm gonna impose P1 minus K1. I'm actually unhappy. Am I correct? Yes, this is good. Yes? So that's what we're gonna get. So my claim is that you get this, and then you will get overall momentum conserving delta function, which is the form of K1 plus K2 minus P1 minus P2. So the difference between the final full momentum minus some of the initial full momentum. And then since you have done the integral over this, you have to get now in the first piece, what? P1 minus K1 squared I, and then you're gonna get another piece where P1, P2 exchanged. Good so far? So that's explicit calculation. Like no-brainer, just use Dyson series. If you do the computation, this is the answer you will have to write. Yes?
The sign of the Q in the first set of function in the integral work because apparently if we insert the Q to P1 minus K1, then the first delta function.
Sorry, are you here?
Left one.
Left one, this one.
And insert, substitute P1 minus K1 to Q.
Yeah,
Then,
so let me get this. Right, because there's a minus Q.
I mean the first delta function.
First delta function.
Yeah.
So you use this to evaluate. When you do that, you basically put, instead of Q, you put a P1 minus K1. So then if you inject, that's the overall delta function. Okay? Good. So now let me tell you even more simplify the Feynman rules. So to do that, I need to define So far we've been computing final S operator initial. But we know that the S operator always includes 1, meaning nothing happens, plus everything else, meaning something happens, right? So the first thing is literally just delta, meaning nothing happens. And then the second one, I times F T transition operator, something happens. And then this thing can always be written as overall momentum conserving delta function. Because physics has to respect the momentum conservation. There's a translation invariance. And then whatever the rest, so which we will use this script notation. A, I goes to F. So it is this one that is invariant Feynman amplitude. Now, if you look at here, in fact, it satisfies the structure. So I times overall momentum delta function, and then the rest. Okay? So let me just write that way. So there's an overall momentum conserving delta function. I times, which is because of I, minus Ig squared, and then basically you have 1 over P1 minus K1 squared minus M squared. Let me drop I to for now, and then flip apart. Okay? So this piece is basically invariant Feynman amplitude. So this will always appear regardless of theory you use, regardless of the process you compute, right? Overall momentum conservation has to be imposed. So now let's revisit that what might be the diagrammatic rules to compute invariant Feynman amplitude. The Feynman rules that I told you before was to compute this entire piece, right, including overall momentum conservation part. There I said that whenever you see the vertex, you have to write that minus I times G times momentum conserving delta function at every vertex. And then for internal line, not just this integrand, we have to integrate over the Q, right? Yes?
Why did you discard the I epsilon in the denominator?
Because I was lazy. Actually, I didn't have a space. I was anticipating it. Okay? Now, let us rediscover actually Feynman rules for just computing invariant amplitudes. So there, the answer is this. So for that, for every vertex, basically you just need to come this, right? You just assign this. However, you make sure that you assign momenta such that they are conserved. Okay? You just make sure that you assign the momenta such that they're conserved. Yes?
It's trying to be related. What is G?
G was the coupling constant appearing in front of this local interaction. The strength that controls this. That's why you see this. Okay?
Yeah.
Now, so what I'm saying is that instead of writing explicitly momentum conservation by hand, we can just draw the diagram such that they already assign the momentum which is consistent with the momentum conservation. Okay? once you have done that, then you can forget about the delta function, just give a minus I times g. And then if you see internal propagator, you just write down 1 over q squared minus m squared plus m squared. Period. So that's now Feynman rules. Okay? And you can say, oh, can I now use Feynman rules to compute this? It's just now 3 seconds, right? Minus ig squared, 1 over q squared minus m squared plus I epsilon, where q in this diagram is what? Like k1 minus p1 or the other way around, right? Done. So you already read off the answer immediately. Good? So it's mnemonics. But also, it is attached to the physics picture. This is the process I want to look at, how to compute it, strength of the vertex, and then I set always the momentum in a way that they're conserved, and then I can write down the internal probability. For scalar, that's all. Good. Now, let's enjoy the physics. Yes?
Why are we dropping the vector I
In the propagator? Yeah, because I was giving you a Feynman rules for just a fi instead of I of fi. So if you were to get the Feynman rules for the I times a of fi, then you have to have I here. Remember, where did the I go away? There was I right here in the propagator, right? But that amplitude was for I times delta function times I times this. Then you have to have that. But if you're interested in just computing this, just 1. So it's up to you. It's not a fixed rule. I mean, it's not that you have to compute this or versus you have to compute this. You just need to know which one you're computing. But in usual textbook, they're gonna tell you, in order to compute I times amplitude. So if you look at the Pascal Schroeder, or it's I times n for him, then Feynman rule it has I. So probably it's a good comment that you asked. Yes.
If we have a propagator more than 1, then I think we should not get rid of that I.
Good. So therefore, let's just stick to S metrics and then only the non-trivial part of it. Let's include I all the time. Then the propagator, let's just keep I all the time. Okay. Here I was explaining where the final rules come from possibly, how you can extract that. Okay. Good. So therefore, at the level of I times invariant amplitude, this is the final rule, including I in the denominator, sorry, numerator of the propagator. Any other question? Yes.
In the process, we calculating the amplitude of some process, some scattering process. We integrate out x1 and x2, which is the vertex point of interacting interaction. Then, is it meaningful to figure out the sequence of each process? I mean, for example, we have some scattering, and we can draw Yukawa line like this or this.
Yes.
Then is it meaningful
Good.
to figure out that sequence?
Yes, very good. So let's actually talk about that a little bit, because that's now you're going into the physics part, actually, right? What does that actually mean? Right? Why we had to do that? What each of these actually physically mean, right? And then eventually, what's the physics that is encoded in this particular amplitude? So let's talk about that. So here, since we are here, let me already talk about that aspect of it. So we are talking about a process where I imagine a perfectly well-defined momentum eigenstate in initial state, right? Which means that they are maximally spread in the position space by uncertainty principle. So there's no notion of like this guy actually made it precisely at x1. It's hard to define. So in that sense, to be consistent with the uncertainty principle, you should be maximally uncertain about exactly where in the space and time this thing actually happens. Okay? And in this formalism, the way to guarantee that to happen is that you have to the sum of entire possible points in space and time. And it is done. So in that sense, it is consistent. And it, like you said, point by point, you might say this vertex happens temporal-wise first and just split it into, and later it meets with this guy. Or it may be the other way around. Or maybe simultaneously, or everything happens. And we cannot tell. Given this preparation of initial state and the collision happens, we cannot tell whether this actually comes from a sequence of this happened first and then later meet, or vice versa, or simultaneously. We cannot tell. So that's why we have to integrate over completely, and we only get well-defined function of only a momentum. So that's sort of physics behind this. Okay, so one more step of physics. So let's actually move on and do it. But if you have a question at this level, do let me know. So let's discuss physics. I guess I summarized enough, right? The entire thing. So you know what to do. Okay, so let's talk about physics. So to do that, let me write down the answer, and then we're going to discuss physics. So minus g squared, because I squared the minus ig squared. And then k1 minus k1 squared. You might say, oh, it was a k1 minus k1, it doesn't matter. It's squared. k2 minus k1 squared, I don't like it, so I can do this or so. So the first thing first. So physics point number one. So this is a manifest that I have written is a symmetric under this too. Well, you should also be able to see that this is also manifestly invariant under this exchange, because by momentum conservation, P1 plus P2 is equal to K1 plus K2. So whenever you see P1 minus K2, you can always rewrite in terms of K1 minus P2. So now if you plug in a square, obviously, by using this, instead of that, you see that this manifests invariant to P1, P2 as well. Okay? So it encodes okay, so you should be able to see that. Physics point number two. So in order to really understand what is the Poisson space physics picture, so one way to do that is that we are going to pick a given reference frame, which is useful for us, okay? Because we are talking about Lorentz invariant physics, which means that we have given a right to choose whichever frame I like to manifest the feature of physics we want to see. So we're going to choose a frame. That frame, often chosen in this context, is called the center of mass frame, but actually more precisely, it is the center of momentum frame. So here, we have this picture in mind. So I have a particle coming in, P1, P2, something happens, and then K1, K2 comes out with a certain angle theta. Okay, so that's what happens at the LHC. So that means that now for momentum P1, I can choose as an energy of n, and then momentum going in some direction. Let me call that to be unit vector E hat. Then P2, because I'm drawing this way, E2 minus PE hat. This goes the opposite direction. But since these two have the same size of the momentum, that's why it is a center of momentum frame. Okay? So if you add it up, it's zero. So you're actually sitting at the zero of total momentum frame. Okay? It's called the center of momentum frame. But these two have the same mass, therefore actually they have the same energy too. Right? P squared plus M squared. M is the same. So K1 then is the E2, again, because the same side of the momentum, but only switching the angle, E hat. K2, again, same energy, K, E hat. Okay? I have chosen a specific frame, which is useful for us. So, and let's see then how this thing looks like in this particular frame. So we just need to compute square, which is this minus that, which is 0, P E hat minus E hat prime. So if you do it, I'm doing a Lorentz invariant square. So square of the zeroth component minus square of the special component. So that gives me P square E hat minus prime square. So this is 2 unit vector. So P square and then 2 square of each minus 2 times product of these two, which I call just cosine theta, unit vector. Okay? So minus 2p squared 1 minus cosine squared, and then I'm just gonna define the entire object here. That's a square of momentum transfer. Okay? So I'm just gonna call that to be my delta squared. That's the momentum transfer. So if you are not 100% sure about the physical picture of momentum transfer, I wasn't having initial particle, right? And then it has to split into something. So there should be a momentum kick to do it, okay? There's a momentum transfer happening to do it, okay? So that is encoded by this square of the special momentum, okay? So you can do the same calculation for the second piece, this, and 2 squared. So if you do it, you should get 1 plus cosine theta. And then I'm going to call that to be delta c squared, where the c is now cross channel, therefore cross momentum transfer. Okay, because you crossed either initial or final state. Okay, so it's a cross. Okay, so if you plug in, then our invariant amplitude becomes, there's overall minus sign. Overall minus sign, this becomes minus of delta squared, this is minus of delta c squared, minus, let me drop the epsilon for now. So you should get basically delta squared plus m squared, g squared, plus g squared. Okay, so that's so far the answer. And I dropped the epsilon because this is a manifestly positive thing. And we throw in epsilon because in case you hit the pole, this becomes 0, so I wanted to regulate momentarily. That's why we introduced epsilon. But since this is now manifestly positive denominator, I don't have to do that. Okay, good. So that's what you can compute it in the center of momentum frame. But let's now really try to understand what is the position space picture of this physics. Okay? So what do? Your answer, this is a manifestly function of 2 things. This is a function of a p, and then basically angle. So this is a function of 2 parameters, right? As you see. So delta c is nothing but basically p and theta. So this is a function of a momentum as promised. Does that make sense? Yes, because you collide, and then deflection angle, and then what is the momentum you're shooting into, right? So when you do the experiment, basically you have a 1 control parameter, which is momentum, free momentum of an incoming particle, and then you measure the deflection angle. So those are 2 parameters you're interested in. So this is a function defined in the momentum space. So let's go to the position space by doing the Fourier transform. Okay, so we're gonna do Fourier transformation. Since this function is defined in the 3 momentum space, So we're gonna just perform a 3 spatial Fourier transform. Okay? So here is the pseudo exercise we can first do. Let's just do D3. We want to go back to momentum. So I'm gonna do this. And then we have something like P square. By P square, I really now mean actually spatial vector square. And then we want to do IP vector X. I don't know if this is consistent with the first lecture of the seventh decade. Right? I'm going to use this Fourier transform formula. Let's see. Okay? So long as you're internally consistent, it should be fine. So let's do this Fourier transformation. How do you do that? Well, let's do first thing first. I know there's a 1/2 pi to the cube from this guy. Okay, that's improvement. And then I can split this into, first of all, d phi, 0 to 2 pi, d cosine theta minus 1 to 1. And then this is a d3p, so I know dp p squared, okay? And then p squared plus m squared e to the minus IPR. So let me now just rewrite this as a PR cosine theta, PR cosine, oh my god, theta, I have done it. Alright, so let's do first thing first. So this is easy to do. I can do immediately. So that gives me 2 pi square. And then let me just to get rid of this cosine integral by actually doing it. I think in my note I had a plus here. I somehow remember it was plus. But it doesn't matter, I think. It does not matter much. So anyway, if I do it, what you're gonna get? So I have now dp p squared over p squared plus m squared integral from 0 to infinity. Remember, this p is the size of the 3 momentum. Okay? Then I do this polar decomposition. And then I'm going to get 1 PR e to the I. So I have to do IPR minus PR. So I just did the cosine integral. Okay? Now, what I can do is that for the second term, I can literally do change of variable. So p to minus p. So when I do that, this basically will have the effect of sending this to minus infinity. Okay? Good. Yes.
See, that set is different from that set, right?
This set theta. In principle, but I can choose a, so this is a relative angle between momentum direction and whatever the x direction I have chosen, right? And then I can choose, so yes, so if I choose this to be my x direction somehow, that is coincided, but in general, you're right that they are not the same. In fact, once I perform the integral, it goes away. So it's actually double variable. Okay? But that theta actually appears, anyway, so it's double variable. Good, so then what do I get? I get 2 pi squared minus I 1 over R integral minus infinity to infinity 2p p 1 power of p is taken care. So this is what I have to do. Yes? Okay, so let's do it. If the integrand are completely regular versus whether there's a singularity, you can think about it. As a general trick, we go to the complex plane of this P. And this integrand has 2 simple poles. So this one has a plus IN and then minus IN. And then the integral has to be done along the real axis. Now you have a temptation of closing this thing. So you have a two binary choice, up or down. Up, who thinks it should be up? Who thinks it should be bottom? For sure, like you said, damn sure, bottom. Down, down. No? Why? So if I introduce imaginary part, P is equal to P real plus I P imaginary part, right? So this I becomes minus, so this is regulated, meaning exponential dies out if I choose a positive imaginary part, which means that I need to close up. Good? So that's a happy loop because this is according to the right thing, so there's this plus of whatever calculation I need to do. If it were the other way around, I have to put additional minus sign, right? That's good. And then I can use residue theorem to finish up this calculation. Okay, so let's do it. Minus I 2 pi squared 1 over r. So residue theorem. So 2 pi times I times residue at plus IM. So that's what I have to do. Yes? And this residue sitting here, so here, basically I have a P plus IM, P minus IM denominator, and then P e to the IPR. And then I just need to evaluate with respect to this pole. That's what I'm doing. So residue is everything else that I need to read off. So that will be 2mi IM. Wait, yes. Okay, e to the minus mr. So mi cancel nicely. There's a 2, there's 2 pi, I minus I plus I compute this plus to be 1. So I claim this should be 4 pi r e to the minus mr. Good? So now we can just literally do this, right? Instead of a p squared, I just literally using delta. But everything else is the same because I'm anyway doing the formula the same, exactly same Fourier transform. So given this invariant amplitude, if you do the Fourier transform to understand the again Hodge space picture, you should get the following answer basically. You get a g squared e to the minus mr over 4 pi r. So you might as well call this to be your potential as a function of r. Yeah? And then you have a cross term. So to write this cross term, let me define, and then we're gonna just look at this and discuss a bit of physics. So to talk about this cross term, basically what it does is that if I had a particle 1 and 2, I'm just swapping this, right? So I'm gonna define a crossing operator epsilon, such that if I had a upside R1, R2, so there was a 2 particle, and then you have to do the other way around. So basically epsilon inside R1, R2 is gonna do plus, because I'm dealing with a bosonic particle. That's what it's gonna do. Okay? So given the potential, this cross term is basically epsilon acting on the potential. That's what it does. And plus, because it is bosonic interaction. Okay, so what is the physics? So to understand the physics, basically, we just need to study this carefully. Okay, so let's talk about one by one. First of all, strength is proportional to g squared. That's trivial fact, but not so. Okay, so whatever the vertex has a strength, it's the square of that thing. And this not only tells you that it's not an absolute answer. In principle, you can have a higher order corrections if you start computing higher order corrections. But this tells you that you look at the effect, physical effect, the leading order in the perturbation theory. So that's the first fact. This is leading order contribution. So leading order divided along. And the second feature, let's actually look at it. So V of R is proportional to. So what it does. So let's actually look at it. So let's break it up. So if I look at a distance scale, this is distance, which is much, much shorter than 1 over m. Okay? Because in principle, you can rethink this in terms of R divided by some range of the force, where R is 1 over m. So given a particle mass which getting exchanged between two ends, okay, there's associated length scale, which let me call it capital R. Okay? And so therefore what I'm asking here is that if I look at the distance scale, which is much shorter than a characteristic distance scale controlled by the mass parameter of the exchanged particle, then what happens? Basically, I'm saying that the R, it goes to zero limit, right? Another way of saying it is that I'm looking at the engineering energy of this collision, which is much greater than m. Because by uncertainty principle, distance is inverse energy, vice versa. Okay? So if I collide a particle at energy or momentum transfer much larger than the mass of the exchanged particle, that's what I'm asking. Then, basically, mathematically, if I just take the limit where R goes to zero limit, it's just asymptote to basically 1 over R, because the exponential factor becomes almost to 1, unity. And this is a characteristic of a long-range force. Newton's law, Coulomb's law, whatever. So there's a characteristic length scale, capital R, controlled by the exchange of mass. If I collide things at a much shorter scale or at much higher energy, it feels like there's almost a long-range force now mediated by almost a massless particle. In the case of gravity, the reason why you get 1 over R potential is because a graviton is massless and it's getting exchanged. In the case of Coulomb force, you get a 1 over R potential because it's a photon which is massless. So if I perform this experiment with energy budget, which is much larger than the mass, obviously, I'm the king, you're nothing. Basically, I can ignore your mass. And you should behave like massless propagator. And then you get this long-range behavior. On the other hand, if you start probing distance greater than R, which means now you're colliding things with energy which is not quite matching the size of the mass itself, now mass effect becomes important. And so in this case, you are genuinely experiencing exponential dynamic behavior. Meaning, at some distances away, they're completely screened out, and you don't get to see that. And what's the physics of this? Which already you understand. How do this n interact with this n? Right? That's the question. How this guy know about this guy? So if they come in with energy, which is smaller, they are not quite easily capable of producing this pi. They get exchanged between those two. They have a hard time interacting with each other. How hard it is? Well, where you have to suffer Boltzmann suppression. I have this much of energy. Can I nevertheless produce this guy so that we can actually communicate? But then you have to make use of a sort of a Boltzmann-Taylor effect. In this case, quantum effect. So it's getting harder to actually produce pi exchange. Only then this guy will say, oh, I see, you are there, right? So now this exponential suppression is manifestation of the fact that you start having less energy accessible to be able to produce pi. Oh. Is that time correct? Yeah, 2 to 2. Anyway, so and this potential is known as Yukawa potential. This type of potential is known as Yukawa potential. Okay, I should have. All right, thanks for your attention. There will be time.